Hi, this is Group 14 presenting the second demo of Geomon. In the first part, Brandon will present the battle mechanism.
Hello, this is Brandon, and I will show you how our system's threading design operates in the battle system. From the map, the user taps on the Home Fragment's monster marker. The Home Fragment receives a tap to read the monsters tagged on the marker and starts a battle activity. On the map fragment, it passes both the player monster ID and the enemy monster ID through the intent extras. The IDs are resolved into full monsters and move objects using our JSON conversion to the repository and Firebase helpers. Our UI runs on the main thread. This includes main activity, home fragment, and the battle activity as shown on this diagram. All of the map drawings, button clicks, and health bar updates happen there. Inside battle activity, the battle system loads full monster data for UI elements like the moveset buttons, names, and battle stats. For example, these are the two JSON files that it's extracted from. This work runs on the background threads with coroutines and dispatcher.io. The battle utilizes the repository files for type, chart, damage calculations, the starting attack, and the attack's physical and special split. To maintain a turn-based file system, we use coroutines with small delays for the main thread. After attack, we delay and then show the next monster's turn on the announcer. The name and damage are displayed on the middle of the screen. For example, the enemy's monster called Electricoon used Storm Surge, which is a move that was on the JSON file. Overall, my battle implementation keeps turn logic and damage calculation on the UI side, while all storage and network stays off the main thread.
Hi, this is Ming. Following Brandon's explanation of the battle mechanism, I will now explain the map, the location service, the capture system, the monster spawning mechanism, multiplayer, Firebase real-time database, and authentication developed by Ming and Long. So let's start with the demo. Since the UI guy in our team is still busy with his work, we currently have a very basic UI where the blue marker represents me, the player. The green markers represent the wild Pokemon, and the red one represent the other player, which I simulated using my second device here. Okay, so from the menu, I can change my username from Ming to like Ming123 and save, and it will be automatically in the Firebase. I can also check the Pokédex, which are the Pokemon I have right now. These three. So currently the Pokemon are spawned if a certain radius surrounding the player has less than 10 Pokemon, and if we try to move around like this, okay, like this, you will see that the new Pokemon will be spawned. Yeah, like this one. Okay, let's stop. Okay, and so while Pokemon are synchronized between different player screens through the Firebase real-time database. So now let's try to capture the Pokemon. Here, so if we try to capture the Pokemon at the beginning when it has full HP, it will be hard because the probability is low, and the Pokemon will have the turn to attack us. And if we try to reduce its HP like this and capture it again, it will be easier since the probability is much lower. And the new captured Pokemon is displayed in my Pokédex right here, which is level 18, quite high. So now let's go to the thread design. Like Brandon explained, the main activity for map and battle activity are displayed in the UI thread, and all the markers update also happen in the UI thread. We have the message handler here to send the data to the location service, which will be explained later. Let's go to the background thread. At the beginning, we run a seeder to parse the species and skills data from the JSON file that we gather. This is done in the IO thread. We also communicate with Firebase to fetch the Pokemon around the player, and if there are not enough Pokemon, we try to spawn them with the random species. Part of this is happen in the Firebase thread, but another part, like mapping the Firebase Pokemon to the local Pokemon data class, is in the UI thread. This will be more clear soon. For the parse species data, we have the room entity species data class and add them to it. This make it more convenient for us to initiate the Pokemon anywhere in our app without having to parse the data again. And the species DAO and repository is for room database operation with species. And so our monster data class is a special one because it's not on room database. We have data representation for monster on Firebase, this one. And we use this class as the middle interface to either initialize or fetch the Firebase monster data and map them to a local monster object for convenience. We also map things like monster sprite here from the sprite URI store in Firebase. The result of Firebase fetch listener is ran on the main thread. Okay, so now let's move on to Firebase. I'm not exactly sure what threads they are using since there is a layer of abstraction between Firebase and us, and we are only using the data reference and listener provided by Firebase. So I will assume that it has an internal worker thread pool. Here we communicate with Firebase to either get or initialize the all the monster and user data. The user data class here is used for multiplayer, like shown in the demo. For now, we don't have any IO operation with user, so that's why we did not put it in the previous IO section. How this works is, first we use Firebase anonymous authentication to create a new user every time the app is run. If the app is run on the first time on the new device, we can add Google or email password sign in later, but for now we think this is more than enough for testing. So we take this user UID of anonymous authentication and we create a new user data object in the real-time database with that ID. And each user has the last active field to know if if there is an online player in the surrounding of the current player, latitude and longitude to synchronize between different player screen, and the list of monster ID, which are the monster that the player has captured. And for a monster, we have a basic stat, latitude and longitude for synchronization, the skill, sprite part, and also a field of owner ID, which is the player that own it. And for any monster that does not have a owner ID and this field is set to null, we identify them as the Y monster, and they are displayed on the map for the user to capture. Okay, so the last part is the location service we use for map. We implement this similar to the myruns activity with a binder and the message handler mentioned before. Okay, so for the demo 2, Brandon continued to work on the battle system, and Ming and Long implement the Map interface, a local service capture system, monster spawning and multiplayer and all fire-based operation. Thank you.